It is section 8.2, K-means and K-methods clustering. Let X be a dataset of n objects and K the number of clusters to form. Given X and K, the clustering algorithms will organize the objects into K partitions where each partition represents a cluster. The clusters are formed to optimize on objective function so that objects within a cluster are similar and objects of different clusters are dissimilar. Here we start with the K-means clustering. It is a partitional clustering approach. Each cluster is associated with a centroid so that it is a centroid-based clustering method. Each point is assigned to the cluster with the closest centroid. The number of clusters K must be specified by the user. Here is the algorithm. That is called the Lloyd's algorithm because Lloyd invented it. And also it is known as Voronoi iteration. Here, first select K points as the initial centroids, and K must be specified, and then the initial centroid must be given. Then we repeat this number 3 and number 4. Form K clusters by assigning all points to the closest centroid. And so that clusters are made, and for each cluster, now recompute the centroid. And we do this computation repeatedly until the centroid don't change. Here we'll see picture. Okay, here red dot is initial centroid. Now in iteration, this initial is given so that points are assigned to the cluster. So this line segment is bisection of that line segment, so that is bisecting line of that point and that point. And also this line segment is bisecting here this and that, and so on. So for this initial centroid, and points are assigned and organize the clusters, and for each cluster now we recompute the centroid. So that is a recomputed centroid. The cross indicates recomputed centroid. Now after finishing one iteration, in second iteration, now there's red dot is initial centroid, which is the same as here now recomputed centroid. After finishing one iteration, there will be now initial centroid. For that one, again, we assign, we reorganize the clusters, and for new clusters, again, we recompute the centroid, so that is now recompute to the centroid. Okay, and we keep going, and after iteration 3, now yet centroids are changing, but after 15 iterations, now centroids are not changing, so it is converged. Okay, that's the idea. Along with this Voronoi diagram, we can see the idea of the K-means algorithm. Okay, here we'll see some detail. Initial centroids are often chosen randomly. The clusters produced vary from one run to another. That means that depending on the initial choice, initial centroids, the result can vary. Now, the centroid is typically the mean of the points in the cluster. And closeness is measured by your Euclidean distance, and usually we are using Euclidean distance, but some other, like a cosine similarity and correlation, can be used, but in majority, the Euclidean distance is being used. The k-means will converge typically in the first few iterations, but it doesn't mean that there is really optimum one. It is anyway converging to a local minimum, so it doesn't have to be global minimum. But anyway, after a few iterations, it converges usually. Now, often the stopping condition is changed to until relative few points change clusters, rather than now the centroids don't change. So that along with this new stopping criterion, you can finish the computation a little bit earlier. And even though you do very complete computation, it's not much changing. So that relatively few points change clusters, that means that the centroid also changes small. So that once the change is small, then you can stop. Here, the complexity is order n times d times k times I, where n is the number of points in the data set, d is the number of features, and k is the number of clusters, and r is the number of iterations. You can easily understand that complexity. Okay. Now, here, evaluating the k-means clusters, and most common measure is sum of squared error, SSE. Now, mu I is the center of ith cluster, Ci, and now X is chosen from the ith cluster. So each cluster, we try to measure variance and sum over the all clusters. That's the sum of squared error. And here, because different initial centroid will make different results, and also initial centroids are chosen usually random way, so that then each one will make a local minima, so that we may try to run multiple times, then we can get multiple sets of clusters. Each one will make a set of clusters, and so after multiple runs, we can get multiple sets of clusters. Among them, we can choose the one with the smallest error, smallest SSE. Now, one easy way to reduce SSE is to increase K, the number of clusters. However, a good clustering with smaller K can have a lower SSE than a poor clustering with higher K. That means that if you have really good clustering, then the SSE is much lower. Okay. Now here, I'll try to explain this first sentence. Okay, if you increase K, the number of clusters, then SSE will be reduced. Okay, here, let's assume we have here search data, and whole data has this part, and another part like that. If you are choosing, for example, K is 2, then now, for example, one cluster can be this one, so the centroid will be that one. And here, for these two portions, maybe centered will be this one. Then if you try to measure the variance, then from this one you have to measure the distance square. The squared error must be summed so that the variance from this portion will be large. However, if you choosing k 3 larger than 2 so that k is increased to be 3, then in this case one cluster can be here, another one can be here, another can be here, so that now the variance of each, the sum of these two variances will be smaller than the earlier and now one variance with the centroid here. So that once you are choosing k larger, then the SSE will decrease. In extreme cases that if we choose the k, the number of cluster, same as the number of points, then each point will be one cluster. Now, in singleton cluster will make the variance 0, so that eventually the SSE will be 0. So the larger the k is, the smaller the SSE is. Okay. The k-means is heuristic to minimize the SSE. So you have to elaborate to get good clustering. Here, okay, this is one example now. And in iteration 1, for this data set, here, initial centroid is chosen here, here, here. And now in second iteration, the centroids are moving, and so that it is adjusting really good way right now. And after 3 iteration, it is now spread. And fourth iteration, it is given in this way. And in 5 iteration, so here is really good spreading centroids. And here in 6th iteration, here we can see really good the clustering. Sometimes it can happen. Okay, here, problem with selecting initial points. The chance of selecting one centroid from each cluster is small. Once you can choose one centroid from each cluster, then the convergence is fast, and then also you can expect good clustering. But the chance is very small here. And also, the chance is relatively small when k is large. And here we have, assuming that the clusters are same size n, and we can compute the probability. That is the number of ways to select a centroid from each cluster. And now here bottom is the number of ways to select k centroid. So that is the probability. For example, if k is 5, then it becomes this one. So that there is about 3.84%. And if k is 10, then now is way smaller. Okay. Sometimes the initial centroid will readjust themselves in right way, and sometimes they don't. Okay, with the same data set, now here, and start with this 3 centroid, and yeah, that is more spread than earlier initial centroid. Here in this one, and centroid is now a little bit dense and accumulated one position, but it is readjusted in the right way. But here, it is a little bit more spread. However, now this centroid is put together with iteration, And now the other one is now making a cluster combining seemingly two clusters, so that it's not well working. Okay. Here we consider solutions to initial centroid's problem. And one way is multiple runs. It helps, and even though you do multiple runs, and yet it's not guaranteed to get global optimum, so that the probability is not on your side. And sample and use hierarchical clustering to determine initial centroid, along with a small data set. And by using hierarchical clustering, you may try to decide initial centroid. So once your initial centroid is chosen very accurately, then you can get good clustering. This is one way. But again, because depending on how data sets, the samples are chosen, it may result in something else. And also another way is that you may select more than k initial centroids, and then here later on here merge them. For some near-round clusters you can merge, and through post-processing you can do that. And also you may try to use bisecting k-means, and along with this bisecting k-means, and it's not as susceptible and sensitive to initialization issues. Here we see pre-processing and post-processing. For pre-processing, you may normalize the data. Also, you may try to eliminate outliers. And most cases, outliers and noise makes some big problem, so that as a part of pre-processing, you may try to eliminate outliers. For post-processing, you may try to eliminate small clusters, and they may represent outliers. And also you may split loose clusters, and that means that clusters with relatively high error you may split. Then more clusters are made, then the error will be reduced. And also you may merge clusters that are close each other, then now, and have a relatively low error. Then you can merge two clusters. Okay, this can be done simultaneously, and in this algorithm, the algorithm name is ISODA. ISODA can do this one during the clustering process. Okay, we'll continue in the second part. Thank you.